Hi everyone, and welcome back to physics. Today we're going to continue our discussion on Newton's laws of motion, but we're really going to talk a little bit about the guided practice that deals with the introduction of Newton's laws. Just a little refresher, let's talk about Newton's second law that we will use quite a bit. It's our F equals ma law. Don't forget that our unit of force is our Newton. Our acceleration is in meters per second squared, and our mass is in kilograms. So our Newton is actually equal to a kilogram meters per second squared. If you don't have your reference table out, I would strongly suggest that you have it out for this particular video because I'm going to be showing you another equation that we could possibly use during this video. So let's get right into the guided practice itself. It says circle the correct answer. An astronaut in outer space away from gravitational or frictional forces throws a rock. The rock will gradually slow to a stop or continue moving in a straight line at constant speed. So it says here that we are away from all other forces. So since we are away from all other forces, our object that is in motion will remain in motion unless acted upon by an unbalanced outside force. Well, there's no unbalanced outside force here. Therefore, that rock will continue moving in a straight line at constant speed. The rock's tendency to do this is called inertia. That's Newton's first law. Number two is a little tricky, but you really have to think about it in terms of what's happening here. The sketch shows the top view of a rock being whirled around on the end of a string clockwise. So that rock is moving this direction. If the string breaks, the path of the rock is what? So what is our unbalanced outside force that's acting on the rock, keeping it moving in a circle? That's the force provided by the string. Once that force is gone, we no longer have an unbalanced outside force. So remember, when we no longer have an unbalanced outside force, objects will move in a straight line. So that rock is going to move in the direction of C. Okay? Now what I want you to do is pause the video and try question 3 on your own. Read through it thoroughly, really think about it, and then I'll discuss it when you get back. Hopefully you read through question number 3, read through it thoroughly, and I'm going to go over the answers with you right now. So let's read through this. Suppose you're standing in the aisle of a bus that travels along a straight road at 100 kilometers per hour, and you hold a pencil still above your head. Then, relative to the bus, the velocity of the pencil is 0 kilometers per hour, simply because it's already on the bus that's moving. So we're talking about relative to the bus. You, the bus, and the pencil are all moving at the same velocity. So relative to one another, you're moving 0 kilometers per hour. However, relative to the road, the pencil has a horizontal velocity of 100 kilometers per hour. Because that pencil is on the bus that is moving 100 kilometers per hour relative to the road. Suppose you release the pencil while it is dropping, and relative to the road, the pencil still has a horizontal velocity of 100 kilometers per hour. Of course, even if you didn't necessarily know it was 100 kilometers per hour, use English to help you. It says still has, which means that velocity hasn't changed. This means that the pencil will strike the floor at a place directly behind you, at your feet, below your hand, or in front of you. Well, you and the pencil are on the bus, so it's just like you dropping a pencil when you're standing in a room. So that pencil will land at your feet. Next time, try this when you're on a bus. Don't stand up because you'll get in trouble, but just do it sitting. It's going to drop straight down. Relative to you, the way the pencil drops is the same as if the bus were at rest, or depends on the velocity of the bus. We just discussed that, so it's the same as if the bus were at rest. How does this example illustrate the law of inertia? Well, a body in motion tends to remain in motion as long as no net force is exerted on the body in the direction of motion. And since there's no horizontal force on the pencil, its motion doesn't change. So no horizontal force on the pencil itself, its motion will not change. Okay? So, I want you to pause the video and try question 1 on the next page. Hopefully you paused the video, and here is how to do question 1 for force and acceleration. Skelly the Skater, it's a great name, has a total mass of 25 kilograms, is propelled by rocket power. Complete table 1, and then we'll complete table 2. So we're going to neglect air resistance or neglect resistance for table 1. So we've got our force of 100 newtons. We're going to be using F equals ma. Our force for our first part is 100 newtons. Our mass is 25 kilograms. So our acceleration, solving for our acceleration, we would get 4 meters per second squared for this first part here. If we solved for the second part, we would solve here, and we should have our acceleration is now equal to 8 meters per second, because all we did was change our force to 200 newtons. Our mass remained the same, so our acceleration, if we solve for it, would be 8 meters per second squared. If we had to solve for the next part, we're actually going to be solving for our force. So let me show you how to do that. So we're solving for our force. We've got our 25 kilograms still. We've got our 10 meters per second squared. So we multiply everything and we would get 250 newtons. That's not so bad. Next question, it says complete table 2 for a constant 50 newton resistance. So if our force, if we have a force moving to the right with 50 newtons, and somebody is pulling or resisting that force with the same amount of force of 50 newtons, think of it like a tug-of-war. Are you going to go anywhere? Is this little dot going to move anywhere? No. So our acceleration is 0 meters per second squared. Here's how that would look algebraically, though. So we've got our, and I'm just going to write F equals ma up here. Our force is experiencing a 50 newton resistance. So what this is depicting is that our force minus our 50 newton resistance will equal our mass times our acceleration here. So solving for our acceleration, our equation now is our force minus our 50 newton resistance force over our mass. This is going to be the equation that we're going to use to solve for our acceleration. Now, how did I get that? Again, it's because we're dealing with a 50 newton force of resistance. It's moving in the opposite direction, so our resistance force has to be subtracted from our force itself. So now we can take that information and we can solve for our acceleration here. So acceleration equals 100 newtons minus 50 newtons over our 25 kilograms. So our acceleration would be 2 meters per second squared. And if we solve for it down here for our 200 newtons, subtract our 50 newton force of resistance divided by 25, we would get 6 meters per second squared. So that would be how you would solve for this. Again, this one was definitely a little on the trickier side. Part B was, because we were dealing with a 50 Newton force of resistance. But I just wanted you to think about how this is really working, what this is like. It's like a tug-of-war. You've got forces that are opposing one another, and which direction are they going to be accelerating, if at all. So now, what I want you to do, if you don't have your reference tables out, please take them out, because I want to go over a different equation, an equation that you're going to need to answer the next several questions. So we've talked about it before. We've talked about our acceleration due to gravity, and we've also talked about our first equation, our Newton's law of F net equals ma. Well, we also have our weight force. Our weight force is known as Fg equals mg. Both of these equations can be found in your mechanics section on your reference tables. And I just want to show you how pretty much identical they are. So, acceleration, so if we just take a look at this top equation here. F net equals ma. Our acceleration equals our net force over our mass. Pretty self-explanatory equation. However, if we take a look at the equation on the bottom here, we've got our acceleration due to gravity, which can be found right on the front of your reference tables, 9.8 meters per second squared. That's our acceleration. So g and a are both accelerations. The only difference is that your acceleration due to gravity on Earth is a constant, found right on the front of your reference table. Fg, instead of being net force, we now have our weight force, or our force due to gravity. Because weight force, when you weigh something, it actually deals with the force of gravity on your particular amount of mass. M still stands for mass, so these are identical equations. We just, instead of talking about a net force, we're talking about our weight force, and instead of talking about any type of acceleration, we're talking about our acceleration due to gravity itself. Okay, that's the only difference. Nothing too major, same exact equation, except now we're talking about our weight force. So anytime you see weight, you know you're talking about our force of gravity. And anytime that you're dealing with g, you know you're talking about your acceleration due to gravity, which is found on the front of your reference tables. So now what I'm going to do is I'm going to go over how to do question number 2 using the weight force. So let's read through this. Block A on the horizontal friction-free table is accelerated by a force from a string attached to block B. B falls vertically and drags A horizontally. Basically what that means is B is falling this way, and as B is falling, A is moving to the right. Both blocks have the same mass of m. So that means that A has a mass of m and B has a mass of m. The mass of the system, A plus B, is, so if each of them contain a mass of m, the system overall must have a mass of 2m, A plus B, so m plus m. Or M&Ms, which are gloriously delicious, only if they're the peanut kind. Regular ones, those are silly. The force that accelerates A plus B, the force that accelerates A plus B is the weight. So the weight force means that we are talking about Fg. Things I want you to think about. Fg means our force of gravity. Which one of these is being accelerated due to gravity itself? Is it A, who's moving horizontally? Or is it B who's moving vertically? Well, which direction does gravity always work? Vertically. So our acceleration due to gravity is actually pointing in the vertical direction, and it always points straight down. So which one of these objects is being accelerated due to gravity? That would be block B. So the force that accelerates the system of A plus B is actually the weight of block B itself, because block B is the object that is being accelerated due to gravity. The weight of B is what? So let's think about this. Weight, remember, our weight force, Fg equals mg, or G equals Fg over m. Same equation, I just rearranged it. So the weight of B is m, and the acceleration that it's experiencing is our acceleration due to gravity. So our weight of B is mg. And the acceleration of A plus B, okay, is it going to be less than g, or more than g? Well, we can definitely rule out that it's not moving at several g's. That's silly. So it says that it is a friction-free table, neglecting the string's mass. Okay, the acceleration of A plus B, yes, it's friction-free, but it didn't say that this little pulley was friction-free. So it's going to move at less than g, just slightly less than g. And use A to show that the acceleration of A plus B as a fraction of g. Now that is a very weirdly worded question. So I'm going to actually clear all of the strokes here, all of my writing. So use A to show that the acceleration of A plus B as a fraction of g. Well, let's write all of our equations that we're going to be using. F equals ma, and Fg equals mg here. So this is our weight force, and this is our net force. Same equations, again, just different types of forces that we happen to be looking at. So, we determined that the weight of B was mg. I'm just going to circle all of our answers again. We determined that the weight of B was mg. So, that means that our force, because weight is a force, that means that our force in our net force equation is equal to mg. Because we determined that the weight was equal to mg, and weight is a force. So it says the force that accelerates A plus B is the weight of B, so that means once we determine the weight of B, we can substitute that in for the force. Our mass of the system is 2m. So we're going to plug that in for our mass, and let's solve for our acceleration here. So we're going to divide both sides by 2m, and we would get our acceleration is equal to mg over 2m. Cross off m. So our acceleration is g over 2. So yes, our acceleration is less than g, slightly less, exactly half of g. So our acceleration is equal to g over 2. If you didn't understand any part of this, you might want to pause it, rewind it, and try and understand it again. If you did, what you can do is now move on to the next part. So you can pause the video and try question number 3 on your own. Hopefully you paused the video, and here is how to do question number 3. So suppose A is still a 1 kilogram block, but B is a low mass feather or a coin. Compare the acceleration of the system in 2, the previous page, the one that we just talked about, that let's just assume that it is a 1 kilogram block. So let's compare the acceleration of the system that we just talked about to the acceleration of the AB system here. So the acceleration here, because B has less mass, is going to be less. And this acceleration, is it going to move close to 0 or close to G itself? Well, because its mass is so small, the acceleration is going to be close to 0. In this case, the acceleration of B is practically that of free fall, or when we say constrained, constrained means close to 0. So that's what it's going to be. And this is all because the mass of B is so tiny that the acceleration here is going to be far less than the acceleration that it experienced on the previous page. So now I want you to pause the video and try question 4 on your own. Hopefully you pause the video, and now we're going to try question 4. So A is now the feather or the coin, and B has a mass of 1 kilogram. The acceleration of A plus B here is going to be much closer to G, because B is much more massive than A. And in this case, the acceleration of B is practically that of free fall, because A is not putting up any kind of resistance whatsoever. So now, I want you to try questions 5 and 6 on your own. Hopefully you pause the video. Now let's go over question number 5. Summarizing 2, 3, and 4, where the weight of one object causes the acceleration of 2 objects, we see that the range of possible accelerations is between 0 and G. You can't accelerate any faster than the force of gravity, and you can't do anything less than nothing. A ball rolls down a uniform slope. So this is question 6. A ball rolls down a uniform slope. Acceleration, we're going to assume that this is a frictionless surface. Acceleration is constant. If the ramp were steeper, the acceleration would be more. Think about you running down a steeper sloped hill or a more gradual sloped hill. You'd run faster down a steeper slope, probably would trip and fall like myself and wind up rolling and maybe injuring yourself, but that's neither here nor there. When the ball reaches the bottom and rolls along the smooth level surface, it no longer accelerates. Okay, hopefully you got all of those right. If you didn't, you can check out the video again. Now what I want you to do is take a look at our independent practice with Newton's second law. So we're going to be using F equals ma. Here's an example of how to use F equals ma. So you're going to work on these particular types of problems. The only reason why these are here would be to make your answers much easier to go through when you are looking at them. Please give me or given your wanted, your equation, your substitution, and your answer every single time. That's something that I really want you to practice, so please, 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 please do that every time. Again, these variables are only here to make it easier for you when we go over the answers to these problems. And then last but not least, we've got our independent practice applying Newton's second law to motion. So again, give me your given, your wanted, your equation, substitution, and your final answer here. Do not forget to convert your units. Please don't forget to convert your units. You'll notice some of these questions, I give you kilometers per hour. You have to convert those to meters per second. So you have to remember how to do your conversions. Please make sure that you are careful and that you're paying attention to what your units are, or else you are not correctly creating a Newton and therefore cannot solve the problem appropriately. So please be aware of that. I hope you enjoyed the video, and I'll see you for our next video.